The cultural principles displayed at Boston were not unique to that battle, but represented consistent patterns throughout the 101st Airborne Division's combat history. In Normandy, scattered paratroopers fought for days in small groups because regrouping with parent units never occurred to them as more important than accomplishing assigned missions. During Operation Market Garden in Holland, the 101st held objectives for longer than planned operations specified because the mission was to hold until relieved, and they would continue holding regardless of how long relief required. At Bastogne, surrounded by 5 German divisions, the response was identical. Accomplish the assigned mission regardless of circumstances. This consistency demonstrated that airborne culture was not situational adaptation to specific tactical problems, but fundamental identity that governed how paratroopers understood their role. The volunteer nature of service reinforced this culture. Every man wearing jump wings had chosen this path knowing exactly what it entailed. Nobody was drafted into the airborne. Soldiers who wanted easier service could have remained in conventional infantry units. Choosing to become a paratrooper meant accepting that you would fight in the worst possible circumstances and that surrender would never be considered as option. This self-selection created units where every soldier shared commitment to principles that outsiders found extreme or even irrational. Their refusal to admit needing rescue became permanent part of 1,001st Airborne culture and identity. Decades later, this attitude remained so fundamental that it appeared in popular media. The Band of Brothers television series concluded its Bastogne episode with on-screen text, noting that while historians credit Pattern with rescuing the 100, no member of the division has ever agreed they needed rescuing. This statement, appearing in a dramatic production, testified to how completely the cultural principle had been absorbed into divisional identity. Even veterans who were children during World War II and joined the 101st decades after Bastogne inherited the cultural understanding that paratroopers do not require rescue when surrounded, because being surrounded is normal operating environment for airborne forces. The attitude transcended specific battles or wars to become permanent part of organizational culture, passed from generation to generation of soldiers who wore the Screaming Eagle patch. The press coverage of Bastogne created tensions between public perception and how participants understood events. Newspapers celebrated Patton's dramatic dash to rescue surrounded paratroopers, creating narrative of cavalry arriving in the nick of time to save beleaguered defenders. This made excellent copy and fit established patterns of heroic military stories. The men of the 101st resented this characterization because it portrayed them as victims requiring rescue rather than warriors accomplishing mission. McAuliffe repeatedly emphasized in press conferences and interviews that his division never asked for help and never felt they needed rescuing. The only urgent request was for medical personnel to treat casualties, which was logistical support rather than combat rescue. This distinction seemed pedantic to journalists and public audiences who naturally viewed surrounded troops as requiring relief. But to paratroopers, the distinction captured everything essential about their identity and the cultural principles that made airborne operations possible. If paratroopers admitted needing rescue when surrounded, it would invalidate the entire concept of airborne warfare, where small units regularly operate behind enemy lines, expecting to be surrounded and outnumbered. The transformation that Bastogne revealed was not change in German military capabilities or American tactical doctrine, but exposure of unbridgeable cultural divide between military traditions. German forces fought according to Prussian military principles refined over centuries, emphasizing rational calculation, professional competence, and officer responsibility for soldiers' welfare. American paratroopers fought according to frontier warrior tradition, emphasizing individual courage, absolute mission commitment, and voluntary acceptance of death as probable outcome. These traditions produced completely different operational behaviors when facing identical tactical circumstances. German commanders surrounded at Stalingrad had eventually surrendered after extended siege because continued fighting became militarily pointless. American paratroopers surrounded at Bostau never considered surrender because tactical circumstances were irrelevant to mission accomplishment. The contrast illuminated profound differences in how cultures understood warfare, military service, and relationship between soldiers and missions. McAuliffe's nuts reply became one of the most famous military communications in American history precisely because it captured this cultural principle so perfectly. The single word contained entire philosophy of military service that separated volunteers who choose dangerous missions from conventional soldiers serving because required. It expressed contempt for enemy threats that assumed American commanders calculated odds like German officers. It communicated absolute confidence that American forces would prevail regardless of tactical disadvantages. Most importantly, it demonstrated that paratroopers operated according to different rules than enemies expected. Von Lüttwitz offered surrender terms, assuming rational commanders would recognize hopeless situation. McAuliffe replied with word that meant his forces would fight to last man because surrender was never option regardless of circumstances. This communication gap extended far beyond Bastogne to represent fundamental difference in how American and German militaries understood combat operations. The legacy of Bastogne influenced American military culture for subsequent generations. Every paratrooper who earned jump wings after World War II learned the story of McAuliffe's reply and the division's refusal to admit needing rescue. Then narrative became teaching tool for instilling airborne culture in new volunteers. If you want to be a paratrooper, you must internalize principles demonstrated at Bastogne, where surrounded men with limited supplies fought elite German forces to stand still because mission required holding position. No other reason was necessary. No calculation of odds mattered. The mission was everything. This cultural principle, transmitted through training and organizational tradition, created consistent operational behaviors across decades of service. The 1001st Airborne Division earned designation as most deployed division in United States Army, not through superior equipment or tactical innovation, but through cultural commitment to accomplishing impossible missions through sheer determination. That culture traced directly back to December 22nd, 1944, when McAuliffe wrote single word that defined what separated paratroopers from every other soldier who ever fought. The post-war years saw many of the Bastogne veterans rise to prominence in civilian life and military service. McAuliffe himself was promoted to Major General on January 3, 1945, just one day after his Paris press conference. He continued serving in the Army, commanding the 103rd Infantry Division in Europe, and later serving as commander of United States Army Europe. He retired as a full general in 1956 and died on August 11, 1975 at Walter Reed Army Medical Center at age 77. He is buried in Arlington National Cemetery alongside his wife, Helen. Lieutenant Colonel Harry Kinnard, who suggested using nuts as the official reply, Rosato Lieutenant General and commanded United States forces in Vietnam. Colonel Creighton Abrams, who led the relief column, eventually became Army Chief of Staff, and the M1 Abrams main battle tank was named in his honor. Countless other veterans of Bastogne served with distinction in Korea, Vietnam, and throughout the Cold War, carrying with them the cultural lessons learned in those frozen Belgian forests. The German officers who delivered and received the surrender ultimatum faced very different fates. General Heinrich von Lüttwitz surrendered to American forces in April 1945 and spent several years as a prisoner of war. He was never charged with war crimes and lived quietly in West Germany until his death in 1969. Major Wagner and Lieutenant Hanker, who delivered the ultimatum under white flag, survived the war and returned to civilian life in Germany. In post-war interviews, German officers consistently expressed bewilderment at the American refusal to surrender at Bastau. From their perspective, the tactical situation clearly warranted capitulation. The fact that American forces not only refused but continued fighting with undiminished determination represented a cultural phenomenon they could not comprehend within their own military framework. This incomprehension extended beyond individual officers to the Wehrmacht institution. German military planning for the Ardennes offensive had not anticipated encountering forces that would fight to the last man in hopeless tactical situations. The cultural assumptions embedded in German military doctrine, where rational calculation governed command decisions, proved inadequate when confronting American paratroopers who operated according to entirely different principles. The Battle of the Bulge officially ended on January 25, 1945, when Allied forces had pushed German units back to their starting positions along the German border. The offensive cost Germany irreplaceable losses in men, tanks, and aircraft that could not be replaced. The final German reserve had been committed and destroyed in a desperate gamble that achieved nothing. For the Allies, the battle represented the largest and costliest engagement. American forces would fight in Europe, but it also demonstrated the resilience and fighting quality of American soldiers when tested under the most adverse conditions. The glass tube shattered and internal components damaged beyond repair. But the transmitter section survived largely intact, protected by its robust copper construction. At the heart of the transmitter was that copper cylinder machined with extraordinary precision, containing 8 symmetrical cavities arranged around a central cathode. The device was labeled with British military markings and the designation CV-64. It was sealed, self-contained with no external power connections beyond the primary electrical feed and a simple output coupling. The engineering was elegant, almost deceptively simple in appearance. Yet the precision of manufacturing was immediately apparent even to initial examination. This was not experimental equipment hastily assembled in a laboratory. This was production hardware designed for reliability and manufactured to exacting standards. General Lieutenant Wolfgang Martini, head of Luftwaffe Signals Intelligence, arrived at the crash site later that morning. Martini was not merely an administrator, but a trained engineer who understood radar technology. He had followed German radar development closely and was familiar with the theoretical limitations that had guided German research priorities. When he examined the captured equipment, he understood immediately that this was significant. The equipment was compact beyond anything German radar could achieve. The antenna was far too small for operation at frequencies Germans considered practical for high-power applications. Yet this was clearly sophisticated technology, not some experimental oddity that had failed under operational conditions. This was a working system that had been operating successfully when the bomber was shot down. Martini ordered the equipment transported under armed guard to Telefunken's Berlin laboratories. The magnetron was packed with extraordinary care. Guards accompanied the transport throughout the journey. The importance of the capture was immediately recognized at the highest levels of Luftwaffe command. This was not routine battlefield salvage, but a potential intelligence windfall that could reveal allied technological capabilities. Professor Leo Brandt received their covered components on February 3rd at Telefunken's facilities in Berlin-Tempelhof. Brandt, born in 1908, had worked as a high-frequency engineer at Telefunken since 1932. He was recognized as one of Germany's leading experts in radio frequency technology. His team worked through the night of February 3rd and 4th, meticulously documenting the device before attempting any testing. Every dimension was measured. Every component was photographed from multiple angles. Detailed sketches were made of the internal structure visible. Through inspection, port-slot X-ray examination revealed the internal cavity structure and cathode. Assembly. The team worked with scientific precision, documenting everything because they understood they might have only one opportunity to examine this technology. What they found in those initial hours stunned them. The magnetron was a sealed unit entirely self-contained with no external magnets. German magnetron designs, including Hullmann's patented versions, required separate powerful electromagnets to generate the magnetic field necessary for operation. These electromagnets were large, heavy, and required substantial electrical power. This device had permanent magnets built into its structure, integrated directly into the copper block housing. The magnets appeared to be made from cobalt steel alloys, materials that provided magnetic field strength. German researchers had considered impossible to achieve with permanent magnets. The engineering was elegant to the point of appearing simple, but the precision required was extraordinary. Tolerances were measured in hundreds of millimeters. The 8 cavities were machined into solid copper blocks, not assembled from separate components. Each cavity was identical to the others within measurement precision. The cathode running along the central axis was coated with an oxide compound that German researchers recognized as an electron-emitting surface, but of A-type German industry had not successfully manufactured. The vacuum seals used techniques that German manufacturers had attempted but not mastered for production units. Every gasket, every junction, every mechanical interface showed evidence of manufacturing processes refined through extensive production experience. On February 4th, Brandt's team prepared to power the magnetron. They built a custom pulse generator to provide the high-voltage electrical pulses needed for operation. The team had no documentation, no operating instructions, no specifications. They had to infer the operating parameters from examination of the device and from general principles of magnetron operation. They expected, based in German experience with magnetron development, perhaps 100 W output at best, possibly at frequencies around 500 MHz. They thought they understood the limitations of the technology. When the magnetron was powered for the first time in a German laboratory, it produced approximately 10 kilo of pulsed power at precisely 3 GHz. The output was stable, repeatable, and far exceeded what German theory predicted as possible. The measurement instruments available in the laboratory were designed for much lower power levels. They had to improvise measuring techniques using attenuators to reduce the signal to levels their equipment could handle, then calculating back to determine the actual output power. Every measurement confirmed the same incomprehensible reality. This thumb-sized device generated more microwave power than German laboratory equipment filling entire rooms could produce. And it did so with an efficiency German theory suggested wasn't attainable at these frequencies. Brandt wrote in his initial report, preserved in German archives and later captured by Allied intelligence teams, that the British had achieved in practice what German mathematics declared impossible. The report's tone was professional, clinical even, but the implications were clear to anyone who read it. Germany's understanding of microwave physics was incomplete. The theoretical frameworks that had guided German research had led them away from a technology that was not only practical, but had been in operational use by the enemy for an unknown period. Engineers measured the magnetron's performance over several days of testing. The output frequency was remarkably stable, varying less than 1% across multiple tests. The frequency stability was achieved through the physical dimensions of the cavities themselves, which acted as resonant structures. German magnetrons using Holman's design suffered from frequency drift as the device heated during operation, thermal expansion, changing the electrical properties of the oscillating system. The British design minimized this through careful engineering of the mechanical structure and choice of materials with appropriate thermal expansion coefficients. Every measurement revealed another layer of sophisticated engineering. The wavelength was equally shocking from a military application standpoint. 90 mm corresponded to 3 GHz frequency. At this wavelength, a small antenna could provide resolution that would require antenna arrays tens of meters across at frequencies Germany used. The implications for airborne radar were immediate and devastating. The British could build radar systems compact enough for single-engine fighters, with resolution fine enough to detect individual buildings from high altitude. They could create ground mapping, radar that showed coastlines, rivers, cities, and terrain features with clarity impossible at longer wavelengths. They could detect submarine conning towers, night fighters, and ships with precision that made German longer wavelength radar seem primitive by comparison. German radar development had dismissed centimetric wavelengths as impractical precisely because they could not generate sufficient power. The entire German radar research program had been built on the assumption that high-power microwave generation was impossible or at least impractical for military applications. The British had solved that problem 3 years earlier in February 1940, when John Randall and Harry Boot at Birmingham University produced their first working prototype generating 400 W at 9.8 cm wavelength. By May 1940, they had improved that 2/1 kW. By late 1940, General Electric Company engineers at Wembley had increased output to 10 kW. And by 1941, production magnetrons were achieving over 100,000 pulsate operation. On February 5th, a conference was convened at Luftwaffe headquarters in Berlin. The meeting was classified at the highest level. Present were General Adnot Martini, Professor Brandt, representatives from Telefunen, Siemens, and GMA, the major German electronics firms, plus air defense commanders and Luftwaffe technical staff. The mood was somber. Brandt presented his findings methodically using technical language and precise measurements, but the conclusions were inescapable. The British cavity magnetron represented not an incremental advance, but a fundamental technological breakthrough that Germany had missed entirely. German scientists had worked on magnetron designs. Holman's patents proved German researchers understood the basic principles. But German research had abandoned high-power microwave development because mathematical models indicated it was not feasible within wartime timescales. Resources were limited. Industry was strained. Priority went to improving existing systems rather than pursuing speculative technologies that physicists said would not work. The British had not just solved the engineering challenges. They had been operating centimetric radar operationally for months, possibly years. While Germany remained convinced such technology was theoretically impossible, or at minimum years away from practical implementation, the conference reviewed what was known about British radar deployment. The Würzburg system had successfully intercepted numerous RAF bombers. Recovery teams had examined wreckage and found no evidence of advanced radar equipment in aircraft shot down before January 1943. This suggested the H-2S deployment was recent, but intelligence from other sources painted a more troubling picture. Reports from U-boat commanders described being surprised by aircraft attacks in conditions where detection should have been impossible. Marine intelligence had noted increasing Allied success in locating surfaced submarines. Luftwaffe bomber crews reported being intercepted by British night fighters with suspicious frequency. The conference participants began connecting disparate intelligence reports into a coherent picture. The British had developed not just one sentiment radar system, but an entire family of applications. Ground mapping radar for bomber navigation, air-toss surface vessel radar for submarine detection, airborne interception radar for night fighters, possibly a gun-laying radar for anti-aircraft systems. Each application used the same basic technology, the cavity magnetron adapted for specific military purposes. The British had not achieved one breakthrough. They had created an entire new category of radar technology, while Germany was still perfecting longer wavelength systems. The captured system was given the designation Rotterdam Garrett, the Rotterdam device, named for the location of the crash. A working group formed immediately, the Arbeitgemeinschaft Rotterdam, abbreviated AGR. The group's mandate was threefold. First, understand how the British magnetron achieved its performance. Second, develop countermeasures against centimetric radar to protect German forces. Third, begin German development of equivalent technology to close the gap the British had opened. Each objective faced substantial obstacles that would prove increasingly difficult to overcome as the war situation deteriorated. Understanding the magnetron required reverse engineering manufacturing processes Germany had not developed. The device used oxide-coated cathodes, requiring specific materials and processing techniques. German vacuum tube manufacturers had attempted to produce similar cathodes, but had not achieved consistent results in production. The British had clearly solved the manufacturing problems through years of development and production experience. The permanent magnets required cobalt, a strategic material Germany had in limited supply. Before Operation Barbarossa, Germany had received cobalt from Soviet sources, but that supply was cut off when Germany invaded the USSR. Turkish imports partially compensated, but supplies remained insufficient for large-scale production. Even the vacuum sealing techniques were unfamiliar to German manufacturers. The magnetron had to maintain high vacuum over extended operating life while withstanding vibration, temperature changes, and mechanical stress of operational use. German vacuum. Tube manufacturing used glass envelopes with metal to glass seals techniques perfected over decades for radio tubes. The British magnetron used all-metal construction with ceramic insulators, requiring entirely different manufacturing approaches. Every aspect of the device revealed engineering refinements that came only from extended production experience. On February 22nd and 23rd, the Arbeitschaft Rotterdam held its first formal two-day meeting at Telefunken's offices in Berlin. Present were representatives from Germany's electronics industry, Luftwaffe technical services, university researchers, and radar specialists from operational units. The group examined the magnetron in exhaustive detail, passing the device around the conference table, taking measurements with calipers and micrometers, making sketches, discussing manufacturing challenges. The atmosphere was professionally subdued. These were experienced engineers and physicists who understood exactly what they were looking at and what it meant. The consensus was sobering. Germany could copy the British design. German machine shops, given proper tooling and sufficient time, could manufacture components to the required tolerances. German material scientists could develop equivalent cathode coatings. German metallurgists could create permanent magnets approaching British performance, but production would require diverting resources from existing programs that were already struggling to meet Wehrmacht demands. Manufacturing capacity for precision components was strained to breaking. Machine tools were operating multiple shifts. Skilled workers were in short supply, increasingly being drafted for military service. Raw materials were allocated months in advance to existing priority programs. Introducing entirely new production processes for unfamiliar technology would take many months at minimum, possibly over a year before meaningful production quantities could be achieved. Dr. Otto Hatchenberg, a young telephone engineer assigned to the issue AGR project, later recalled the atmosphere in those early meetings during a 1973 interview conducted by Woodruff Sullivan for the National Radio Astronomy Observatory. The interview was part of Sullivan's research for his book on early radio astronomy. Hatchenberg, who had worked on recovering and analyzing radar equipment from crashed Allied aircraft during the war, described the psychological impact of examining the British technology. We were examining equipment that proved British engineers had solved problems we had declared unsolvable. Every aspect of the design revealed thoughtful engineering matured through experimentation we had never conducted. This was not prototype equipment cobbled together in a laboratory. This was production hardware, implying the British had been manufacturing these devices in quantity. We were studying what appeared to be the third or fourth generation of their development, while we had not begun serious work on the first generation. The revelation was compounded when interrogators interviewed the surviving crew members from the downed Sterling. Initially, the two prisoners provided only name, rank, and serial number as required by Geneva Convention. They had been extensively briefed on the importance of the H-2S system and understood that no information should be disclosed. RAF Bomber Command had emphasized during briefings that H-2S represented years of British research investment and that its capture by Germany could compromise Allied bombing effectiveness. Aircrew were told that under no circumstances should they discuss the radar system's capabilities, operating principles, or deployment status. However, over subsequent days and weeks, German interrogators skillfully extracted key details. The Luftwaffe Interrogation Center, Averestella West at Oberosel near Frankfurt, employed experienced interrogators who used sophisticated psychological techniques. The interrogators did not resort to physical coercion, which was generally counterproductive with Allied aircrew and violated marked policy. Instead, they used a combination of isolation, seemingly casual conversation, planted false information to elicit corrections, and careful psychological pressure applied over extended periods. From these interrogations, German intelligence learned critical information. The system was called H-2S, though the prisoners did not know the origin of the designation. It provided a map-like display of ground features below the aircraft, showing coastlines, cities, rivers, and terrain. The radar had been in operational service since late January 1943, only days before this particular aircraft was shot down. Most alarmingly, the crew indicated this was not experimental equipment assigned to a few select aircraft. Bomber Command was in the process of fitting H-2S to the entire Pathfinder force initially, with plans to eventually equip all heavy bombers. The prisoners' information suggested British production capacity was sufficient to manufacture these devices in hundreds, possibly thousands. The scale of British sentiment radar deployment became clearer as intelligence accumulated through February and March 1, 1943. Multiple sources of information began converging into a comprehensive picture. Signals intelligence detected H-2 transmissions from increasing numbers of RAF bombers. The distinctive pulse characteristics and frequency range became identifiable. Marine. Reports documented increasing U-boat losses in the Atlantic, with submarines being attacked by aircraft in conditions where detection by previous generation radar should have been impossible. Submarines were being caught surfaced at night in complete darkness, attacked before they could crash dive to safety. The magnetron technology was not limited to bombing radar. Coastal Command aircraft were using centimetric ASV Mark III radar to detect surfaced submarines. The same cavity magnetron that provided 9 cm wavelength for H2S ground mapping could detect submarine conning towers and periscopes at ranges that longer wavelength radar could not match. The narrow beam width, possible at centimetric wavelengths, provided angle accuracy sufficient to guide aircraft directly to submarines before detection was possible using German MTOX radar detectors, which were tuned to detect the longer wavelengths of ASV Mark II radar. U-boat losses in the Atlantic had been climbing mysteriously throughout late 100, 942, and early 1943. Admiral Karl Donitz, commanding U-boat forces, had noted with concern that submarines were being caught on the surface with increasing frequency. U-boat commanders reported being attacked by aircraft that appeared suddenly, providing no warning that allowed time to dive. The MTOX detector, which had previously provided effective warning of approaching ASV-equipped aircraft, was failing to detect these new attacks. The explanation was now clear. British aircraft were hunting submarines using ASV Mark III centimetric radar that German boats could not detect with existing equipment. The coating had to be uniform, adherent, and produce consistent electron emission properties. German attempts to produce similar cathodes had been partially successful in laboratories, but had not achieved the consistency needed for production units. British manufacturers clearly had years of production experience refining the process. German industry was starting from laboratory-level understanding and attempting to reach production-level capability under wartime pressures. Britain had been working with American firms, particularly Western Electric and General Electric, that had decades of experience with vacuum tube manufacturing for communications and broadcasting applications. When Britain shared cavity magnetron technology with the United States through the TESARD mission in September 1940, American .2004 manufacturers had rapidly scaled up production using manufacturing expertise gained through years of commercial vacuum tube production. Germany had strong vacuum tube industry, but it was oriented toward glass envelope construction using Metallto glass sealing techniques. The all-metal magnetron with ceramic insulators required different manufacturing approaches that German industry was attempting to develop in parallel with production efforts. The permanent magnets presented perhaps the greatest material challenge. British magnetrons used cobalt. Steel alloys, likely Alnico type, to create powerful permanent magnets, integrated directly into the tube structure. These magnets provided magnetic field strength of several thousand Gauss necessary for proper magnetron operation. Germany faced critical cobalt shortages that affected all high-temperature alloy production. Cobalt was essential for turbine blades in aircraft engines, cutting tools for machine shops, and various steel alloys used in weapons production. Before the war, Germany had imported cobalt primarily from Belgian Congo and Canada. Sources cut off when war began. Limited supplies came from Finland and Turkey, but quantities were insufficient to meet all military needs. Diverting cobalt to magnetron production meant reducing availability for other military necessities, each with its own priority claim on scarce resources. German planners faced impossible allocation decisions. Aircraft engine manufacturers needed cobalt for turbo supercharger components that allowed high-altitude operation. Machine tool manufacturers needed cobalt steel for cutting tools that maintained hardness at high temperatures. Tank manufacturers needed cobalt for armor-piercing ammunition. Every ton of cobalt allocated to magnetron magnets was a ton unavailable for these competing uses. German engineers experimented with alternative magnetic materials, including various iron-nickel alloys and chrome-steel combinations. None provided the field strength required for optimal magnetron performance. Electromagnets could provide sufficient field strength, but added weight required separate power supplies and introduced reliability issues. The elegance of the British design with integrated permanent magnets, requiring no power and having no failure modes, was impossible to replicate with German materials. In a bitter irony that illustrated the desperate state of German radar development, engineers began salvaging permanent magnets from other crashed British aircraft to complete their magnetron copies. German production units were being completed using British manufactured components cannibalized from battlefield salvage, a situation that underscored the industrial limitations Germany faced. By May 1943, Telefonin had completed 4 LMS-10 magnetrons, painstaking copies of the British CV-64 design. These represented 3 months of intensive work by some of Germany's best engineers and consumed resources from precision machine shops, chemical plants, and material suppliers across German industry. 4 tubes total. Meanwhile, according to captured documents recovered after the war, Britain was producing approximately 200 cavity magnetrons per month by mid-1943, and American production was reaching similar levels. The disparity was not just technological, it was industrial, reflecting fundamentally different manufacturing capacities and resource availability. Germany could understand the technology. German physicists grasped the operating principles. German engineers could design equivalent systems on paper, but Germany lacked the manufacturing base to produce the technology at scale, while simultaneously maintaining production of existing military equipment. The Arbiter mineshaft Rotterdam continued meeting throughout spring and summer 1943, developing detailed production plans, requesting resource allocations, and attempting to overcome manufacturing bottlenecks. But practical progress remained frustratingly slow, as Germany's industrial situation deteriorated under Allied bombing and resource exhaustion. Meanwhile, the AGR pursued parallel efforts on countermeasures against centimetric radar. If Germany could not match British capability immediately, they could develop systems to detect and counter it, reducing the operational advantage British radar provided. The detection effort proved relatively straightforward compared to magnetron production. Crystal detectors tuned to 9 cm wavelengths could pick up H2's transmissions at considerable range. German industry could manufacture crystal detectors using existing technology. No exotic materials were required. No new manufacturing processes needed development. By April 1943, German engineers had developed prototype detectors that night fighters could carry. The system was designated FUG 350 Kano-Z, named after the Greek island Kanakos. The device used a rotating direction-finding loop antenna housed on a teardrop-shaped fairing mounted on aircraft fuselages. The receiver covered the frequency range 2,500 to 3,750 MHz, encompassing the H2S operating frequency. Detection range was approximately 35 kilometers, sufficient to allow night fighters to locate bomber streams that were otherwise invisible in darkness and clouds. Kanos provided night fighter crews with general direction to RAF bombers using H2S. The system could not provide precise range or bearing information, but it allowed fighters to home toward emission sources, then use visual observation or Liechtenstein AI radar for final intercept. Kanos entered operational service in September 1943, first used operationally on September 2nd. German night fighter kills increased as pilots learned to home on H-2S emissions, treating the British radar transmissions as a beacon that revealed bomber locations. However, NACS was fundamentally reactive technology, a countermeasure against British capability rather than an equivalent German system. It relied entirely on British bombers transmitting. If the British turned off their radar or at different frequencies, CNOS was useless. British intelligence soon learned of CNOS through signals intelligence and prisoner interrogation. RAF worried that H-2S was revealing bomber positions to German fighters, possibly causing losses that outweighed the navigation benefits. A detailed analysis was conducted comparing bomber loss rates before and after NACOS deployment. Surprisingly, analysis showed losses actually decreased slightly after NACOS introduction, possibly because H-2S-equipped aircraft could navigate more accurately and spend less time over German territory. RAF concluded H-2S benefits outweighed their risks and continued full deployment. British engineers immediately began developing countermeasures, including 3 H-2S Mark III that would operate outside CNOS detection range. Germanophores a developing indigenous sentiment. Radar moved forward slowly through 1943 and on 944 facing mounting obstacles as Germany's strategic situation deteriorated. Telefunken worked on an airborne interception radar designated FUG 240 Berlin using copied magnetron technology. The system was intended to provide German night fighters with centimetric AI capability matching British systems. Siemens developed a ground-based jammer called Rotorus Intended to interfere with H-2S operations by transmitting strong signals on H-2S frequencies. GEM investigated centimetric early warning systems to replace Freya with more capable technology. Every project faced the same fundamental constraints that would prove insurmountable. Limited manufacturing capacity meant that even when prototype systems worked, production could not be scaled up rapidly. German industry was already operating at maximum capacity, producing existing radar systems, communications equipment, and other electronics. There was no spare capacity to absorb new production programs. Shortage of critical materials worsened throughout 943 and 1944A's Allied bombing disrupted supply chains and cut access to sources. Cobalt for magnets, tungsten for transmitter tubes, special steel alloys for waveguide components. Even basic materials like copper and aluminum became increasingly difficult to obtain in necessary quantities. Lack of experience with high-frequency techniques meant German engineers were learning as they developed systems. Components that British engineers considered standard were exotic rarities in Germany, requiring development programs for each component type. Crystal mixers for receivers required German manium crystals ground and mounted with precision. German industry could not consistently achieve. The crystals had to be contacted precisely to create a metal semiconductor junction with proper electrical characteristics. British manufacturers working with American partners had standardized crystal detector production. German manufacturers were still perfecting laboratory techniques. Waveguide components needed machining, accuracy beyond normal. German manufacturing standards. Waveguides, hollow metal tubes conducting microwave energy, required precise internal dimensions to propagate desired frequencies without excessive loss. Surface finish requirements were more stringent than for lower frequency RF components. German machine shops struggled to meet specifications consistently. Even relatively simple items like coaxial cables designed for centimetric wavelengths were in short supply. American scientists immediately recognized the technology's military significance. American industrial capacity had rapidly mobilized to exploit the technology. The radiation laboratory was established at MIT in November 1940. specifically to develop radar systems using cavity magnetron technology. The lab grew to over 4,000 scientists and engineers by 1943, an organizational scale Germany could not match. Contracts had been placed with dozens of American manufacturers for magnetron production. Bell Telephone Laboratories, Western Electric, Westinghouse, General Electric, RCA, and many smaller firms were producing magnetrons and radar components. By 1943, American industry was producing magnetrons at rates of thousands per month, equipping not just American forces, but also supplying Britain through Lend-Lease. The magnetron that German scientists examined with such care was one of tens of thousands being manufactured. America was incorporating sentiment radar into every conceivable military application. Gun-laying systems like the SCR-584 used sentimentric radar to direct anti-aircraft fire with unprecedented accuracy. Naval fire control systems used sentimentric radar to spot shell splashes and direct gunfire onto targets beyond visual range. Airborne early warning systems using sentimentric radar detected enemy aircraft at ranges exceeding 150 km. Precision. Bombing aids like Lab used sentimentric radar with autopilot integration to automatically bomb through clouds. Each application represented development programs with budgets measured in millions of dollars, exceeding Germany's entire radar research allocation for all programs combined. British sentimentric radar production had expanded from laboratory prototypes in 1940 to industrial manufacturing. By 1942, the GEC facility at Wembley had manufactured the early prototype magnetrons that went to America on the Tizard mission. By 1942, GEC, EMI, Ferranti, Standard Telephones and Cables, and other British firms were producing magnetrons by hundreds monthly. The cavity magnetron had become a production component with standardized designs, interchangeable parts, and quality control procedures, ensuring consistent performance batch after batch. British manufacturers had solved the production engineering problems that German industry was still attempting to overcome. German magnetron development remained in the experimental stage, producing hand-built prototypes that required individual tuning and adjustment. Every German magnetron was unique, built by skilled technicians who adjusted cavity dimensions, cathode positioning, and magnetic field until performance met specification. This was laboratory practice, not industrial production. British magnetrons came off production lines with performance specifications guaranteed by manufacturing process control. Dimensions were held by precision machining. Cathode coatings were applied in controlled processes, yielding consistent results. Magnets were manufactured to specifications, ensuring proper field strength. Testing verified performance, but individual tuning was not required because the manufacturing process ensured consistency. The difference represented not just years of development time, but entirely different approaches to industrial organization and quality control. As German scientists struggled with magnetron production, they also began understanding how far behind they had fallen in related technologies beyond the magnetron itself. Cavity magnetrons-enabled compact sentimentric radar, beaut-effective systems required other technologies equally advanced. British radar used plan position indicator displays, circular cathode ray tube screens showing a map-like presentation of targets with the radar at the center and targets appearing at proper range and bearing. This was far more intuitive than a scope displays showing range and bearing separately. German radar relied in a scope displays because that was the established technology, well understood and producible. Developing PPI displays required specialized CRT tubes, deflection circuits, and signal processing that German radar engineers were only beginning to investigate seriously. In 1943, British systems incorporated automatic tracking using servo mechanisms to keep antennas locked on targets without manual operator control. Once a target was acquired, the radar tracked automatically, maintaining lock-through turns and maneuvers. German systems required manual tracking by skilled operators who adjusted controls to keep targets centered on displays. Automatic tracking required feedback control systems, position servos, and signal processing techniques that German industry had not widely deployed. The technology existed in German laboratories, but production systems remained manually operated. British radar used TR switches, transmit-receive switches, devices allowing a single antenna to both transmit and receive by isolating the receiver during transmission pulses. This eliminated the need for separate transmit and receive antennas, simplifying antenna systems and improving performance. German systems typically use separate antennas or simple switching methods that were less effective. British TR switches use EDGAS discharge tubes that switched in and cons, protecting sensitive receivers from kilowatts of transmitter power. German engineers were beginning to develop similar components in 1943, but were years behind in practical implementation. The most troubling aspect of the technological gap was how it had developed largely invisibly to German intelligence. Germany had excellent scientists, many trained at world-class universities. Germany had capable engineers with strong theoretical backgrounds. Germany had substantial industrial capacity built up through the 1932's rearmament program. Yet Britain, with significantly smaller industrial base and fewer total resources, had achieved decisive technological superiority. In the most militarily significant electronic technology of the war, understanding how this occurred became a subject of post-war analysis that revealed important lessons about technology development and strategic planning. The explanation lay in different strategic decisions made years earlier before the war began. Britain had prioritized radar development from 1935 onward under the direction of Robert Watson Watt and the Committee for the Scientific Survey of Air Defense. Substantial government funding flowed toward our research. The chain-home early warning system was built despite being expensive and technically challenging. Research infrastructure was created specifically for radar development, including the Borsee Research Station and later the Telecommunications Research Establishment. Specialists were trained systematically. Industrial capacity was built up with government support. By 1939, Britain had invested years of effort and substantial resources in radar technology. Germany had also developed radar systems in the 1930s, actually deploying operational systems before Britain. In some cases, the Freya and Wurzburg radars were excellent systems, but Germany had not made radar development the top national priority that Britain had. German radar programs competed with numerous other military technology programs for funding and resources. When war began, German industry focused on producing existing systems rather than exploring new approaches. The Blitzkrieg victories of 1939 to 1941 seemed to validate German equipment and tactics, reducing pressure to develop fundamentally new technologies. The Hitler Decree of 1940, limiting research funding to projects promising results by 1942, had been particularly devastating for long-term radar development. Cavity magnetron development required patient experimental work over multiple years. Gradual refinement of manufacturing processes could not be rushed. Systematic testing was needed to understand behavior at frequencies that existing theory inadequately explained. Such research could not promise definite results. Within the 2-year time frame the decree mandated, German programs exploring centimetric wavelengths were defunded or reduced. In priority in 1940 and 1941, precisely when British programs were achieving breakthrough results, German research facilities were shifted to improving existing systems. rather than developing fundamentally new capabilities. Würzburg improvements, Freya range extensions, Liechtenstein airborne radar development all received priority because they promised near-term operational improvements. Longer-range research into fundamentally different approaches was postponed until after victory, which German leadership expected to achieve through existing capabilities. The decision was rational given German military success in 1940 to 1941 and the apparent vindication of German equipment and tactics. But it conceded technological initiative to Britain at the critical moment when British desperation was driving innovation. By summer 1943, the full scope of Allied centimetric radar deployment was apparent to German air defense through accumulated intelligence from multiple sources. British H-2 precision bombing through weather and darkness that previously scattered bombing effectiveness. Over 200 RAF bombers were equipped with H-2S by mid-1, 1943, with production continuing at rates that would equip the entire heavy bomber force within a year. Coastal Command. ASV Mark III radar was making the Atlantic progressively more dangerous for U-boat, contributing to a crisis that would force Donuts to temporarily withdraw U-boat from the North Atlantic. In May 1943, RAF night fighters with centimetric AI Mark THAAD were inflicting unsustainable losses on German bomber forces attempting attacks on Britain, essentially ending the German strategic bombing campaign. American radar technology was advancing even faster then. British with development programs that dwarfed British efforts in scale. The SCR-584, gun-laying radar using cavity magnetron technology and automatic tracking was achieving anti-aircraft effectiveness, previously impossible. Naval surface search radars. We're allowing American ships to fight effectively in darkness and poor visibility. The Arbatine Shaft Rotterdam continued meeting throughout 1943 and 1944, documenting progress and obstacles, in detailed protocols that survived the war and provided historians with insight into German radar development struggles. Meeting. Minutes show technical discussions of magnetron design, manufacturing problems, materials shortages, and mounting frustration with lack of progress. The protocols reveal competent engineers working under impossible conditions, understanding what needed to be done, but lacking resources and time to accomplish it. Production plans were developed showing how Germany could manufacture magnetrons in militarily significant numbers, if materials were available, if skilled workers could be retained, if bombing did not disrupt production, if enough time existed. None of those conditions could be met. By early 1944, Telefunken had produced approximately 20 magnetron copies, compared to over 10,000 produced by British-American industry. Siemens had delivered a handful of Roderick jammers that were deployed at air defense sites around key targets, but their effectiveness was limited. The Berlin airborne radar remained in extended testing, encountering problems with reliability and performance. Production of operational systems in militarily significant numbers remained perpetually 6 months away, a timeline that kept receding as obstacles mounted. In April 1945, as Allied forces overran German territory from east and west, Telefunken finally began delivering production Fu-240 Berlin night fighter radars. The system used German-built magnetrons based on captured British designs and provided capabilities roughly equivalent to British centimetric AI from 1923 years earlier. About 25 units were installed in Junkers Do-88 night fighters. The war ended in May 1945 before the system saw significant combat use. 3 years after capturing the Rotterdam Garret in February 1943, Germany had produced a system equivalent to technology. Britain had fielded operationally in 1942, and America had surpassed by 1943. The decade gap in radar physics was not metaphorical. It was literal. German centimetric radar in 1945 equaled British capability from early 1942, representing a 3-year lag in calendar time, but reflecting fundamental differences in technological approach and industrial capacity that translated to a decade's worth of development trajectory. The post-war assessment was unambiguous and backed by comprehensive documentation captured by Allied intelligence teams. Dr. Hatchenberg, who had worked on the Rotterdam Garrett project throughout the war, later became a distinguished radio astronomer and colleague of British scientists who had developed the cavity magnetron. After the war, Hatchenberg worked at the Heinrich Hertz Institute from 1951 to 1961, became professor at Bonn University in 1962, and served as founding director of the Max Planck Institute for Radio Astronomy from 1967 to 1978, playing a key role in planning the 100-meter Effelsberg radio telescope. In interviews conducted decades later, he acknowledged the magnitude of the German failure with professional honesty. In a 1973 interview, Hatchenberg stated, "Weck knew the principles. Holman had patented cavity magnetron designs in 1935. We had the theoretical knowledge published in journals. What we lacked was the sustained commitment to develop theory into practice." The British made cavity magnetron development a priority and persisted through experimental failures until they achieved practical success. We calculated that success was unlikely based on our theoretical models and ceased trying. By the time we realized our error through examining the captured equipment, we were years behind and lacked resources to catch up. The gap was not in scientific knowledge, but in willingness to pursue development despite theoretical obstacles. Allied post-war intelligence teams documented the German radar program systematically through multiple operations. The ALSO's mission, tasked with assessing German scientific capabilities in physics and electronics, conducted detailed investigations of German radar research facilities, interrogated scientists and engineers, and examined captured equipment and documentation. The Combined Intelligence Objectives Subcommittee sent teams to examine German industrial facilities and technical institutes. The British Intelligence Objectives Subcommittee conducted parallel investigations. The combined reports painted a detailed picture of German radar capabilities and limitations. The post-war assessments found German radar research sophisticated and effective in areas where Germany had invested consistently. Würzburg. Tracking radar represented excellent engineering within its frequency range. The conical scanning technique provided accuracy approaching theoretical limits for that wavelength. Mechanical construction was robust and reliable. Operational doctrine was well developed. Freya early warning systems were effective for their intended purpose with good range and reliability. German radar-directed anti-aircraft fire was more effective than Allied equivalents using similar wavelength technology. Where Germany had pursued radar development consistently, results were respectable and sometimes superior to Allied equipment in comparable categories. But in centimetric wavelengths, German research had effectively stopped in 1940 to 1941. The ALSO mission teams found German laboratories equipped with captured Allied radar equipment that was being studied when the war ended. German engineers were still analyzing technology. The Allies had moved beyond trying to understand 3-meter systems, while Allied development had progressed to even shorter wavelengths. The gap was not that German scientists were less capable intellectually. The gap was that German science had been working on different problems while Allied science solved the critical challenge that defined the technological trajectory of radar development. The strategic implications were profound and measurable. Centimetric radar enabled Allied operations that would have been impossible with longer wavelength technology. The Battle of the Atlantic turned decisively in Allied favor in 1943, largely because coastal command aircraft using ASV Mark III could detect submarines that German boats could note-vade. U-boats were forced to remain submerged more, reducing effectiveness and requiring battery charging in daytime when visual detection was possible. Strategic bombing became progressively more effective as H-2S and later 3cm H-2X allowed accurate navigation and bombing through weather conditions that would have scattered earlier raids. Night bombing accuracy improved from miles to hundreds of meters. Allied night fighter capabilities decimated German bomber forces attempting attacks on Britain, RAF. Night fighters equipped with centimetric AI intercepted German bombers with efficiency that made strategic bombing of Britain too costly to sustain. By mid-1943, Luftwaffe bomber operations against Britain had effectively ceased. None of these advantages depended solely on radar, but in each case, centimetric radar provided capabilities that German forces could not counter effectively because Germany did not possess equivalent technology and could not develop defenses against capabilities they could not duplicate. The cavity magnetron represented a paradigmatic example of technological surprise in warfare. Germany understood the theoretical principles involved in magnetron operation. German scientists had worked in magnetron designs and had published research in international journals. Hullmann's 1935 patent demonstrated German researchers understood multi-avity magnetron concepts. Yet when confronted with British achievement, German engineers had to admit they were years behind in translating theory into practical high-power devices. The surprise was not that cavity magnetrons worked in principle, which German physicists accepted. The surprise was that they could work at power, levels and frequencies German calculations had deemed impractical for military applications. The British had not just built better equipment through superior engineering, they had demonstrated that German understanding of what was technically feasible was fundamentally incomplete. German theoretical models that predicted magnetrons would be unstable and low-powered at centimetric wavelengths were revealed as incorrect or based on incomplete understanding. British experimentalists had found solutions that German theoreticians had declared impossible. This represented a failure, not just of engineering but of scientific methodology, showing the limits of purely theoretical approaches without extensive experimental validation. The industrial dimension of the technological surprise was equally significant and perhaps more strategically consequential. German engineers eventually learned how to build magnetrons approaching British performance. The LMS-10 magnetrons produced by Telefunken functioned comparably to British CV-64 units they were copied from. German scientists understood the physics. German engineers could replicate the designs, but Germany could not match British and American production capacity. The tens of thousands of magnetrons produced by British and American industry dwarfed German production of hundreds over the entire war period. Allied magnetron production represented industrial mobilization for electronic warfare at scales. Germany never attempted and could not match given resource constraints and competing priorities. Radar tubes were being manufactured with the same industrial techniques and volume production methods used for artillery shells or aircraft. Engines. Quality control systems ensured consistent performance. Standardization allowed interchangeable components. Production volume transformed. Advanced technology requiring specialized expertise into abundant commodity that could be deployed across all military services in numerous applications. German radar remained. Specialized equipment produced in limited quantities by skilled technicians.